permission.
Oh, I can somehow record.
Because now you are the co-host.
Okay, then it's okay. Now I recorded. Okay.
そうだね。スピーカーレコーディング。レコーディン
Okay.
グ。Okay, shall we start?
Yeah, let's start.
Okay, let me start with the introduction. So let me introduce today's speaker. So hello everyone. Welcome to SCU Yao SCU String Theory Semester Seminar today. So today's speaker is Professor Satoshi Nawata-san. He got a PhD in Wisconsin of let's see.
It's okay,
Milwaukee,
Milwaukee,
United States.
and
Yes,
yeah.
Milwaukee, United States, and he is now associate professor in Fudan University,
Yeah.
and he's working on various aspects of mathematical physics and string theory. So today he will be talking about 2D 0,2 dualities from 4D. Please start, Satoshi-san.
Okay. Thank you very much for introduction, and thanks for coming, many people. Yeah. So I'm gonna talk about the 2D 0,2 duality, new example of duality and duality with 0,2 supersymmetry. This talk is based on the work with my students, Jachun and Jaha, last year. But I mean, during the process of the, how to say, referee, the paper grows, and then the paper really complete this year, actually. And yeah, and then Jachun is going to be on market, a postdoc market this fall. So he's brilliant on the calculation, and also like exact computation of the supersync partition function. So if you're interested, please consider him. And the disclaimer is that I personally think 2D 0,2 theories are poorly understood. And then there are much more to be discovered, much more to be understood from various perspectives. And then our paper just made us very, very modest progress, even duality with 0,2 supersymmetry. And really appreciate if the audience could provide some insight about this theory. I personally think I don't have so much tools, so much understanding for this theory. So whatever your perspective, brain or geometric engineering, chiral algebra, 0,2 mirror symmetry, whatever aspect you have an insight or like more perspective you could provide, I would really appreciate. So feel free to stop me during the talk, and then even after talk, if you have some whatever hints you could provide me, just please tell me. I'm desperate to understand this 2D 0,2 theory. And yeah, so that's a first disclaimer. Okay. Yeah. So let's start with some basics of the 0,2 supersymmetry. Supersymmetry theories is missing. So you have 0,2 supersymmetry. So you have two right-moving supercharges. Plus means right-moving, and with Q and Q tilde, which has U1R. It has a U1R symmetry, and it depends on notation plus and minus U1R charges it has, and it has a following anti-commutation relation. Essentially, this is almost like a Hamiltonian plus momentum. And then for left moving, there are no supercharges, so it's a chiral 2D theory. So that's a left moving and right moving intrinsically has a different behavior. And for multiplets, you have a color multiplet which satisfy this condition, which is very similar to anyway some other dimension. Also, you have a Fermi multiplet which has the left moving fermion and the auxiliary field which satisfy the following constraint: E term. It just give you E term. And then there's the vector multiplet, gauge field, and gaugino in adjoint representation. Those are main multiplet if you have a Lagrangian description. And yeah, so Fermi multiplet has a holomorphic constraint by E term, and then standard superpotential is like a J term. This is the Fermi, gamma is Fermi multiplet, and J is the J term superpotential, and then they should satisfy this condition. Okay. Yeah. And then left moving, right moving central charge generically differs. And it has a rich aerodynamics and dualities. And then there are more to discover. Any question at this moment? So main tools at this moment to study 2D 0,2 theory, and also in this talk, I will use the following the tools to study the 0,2 theory. So the most so far powerful how to say partition function is this elliptic genus, which is the in this talk I just consider the Ramon sector, everything, Q to the Hamiltonian, left-wing Hamiltonian, and then ZA is some fugacity for flavor symmetry, and then which is supposed to be invariant under the deformation of the theory. And then, yes. And then if you have a Lagrangian description, you can write down each contribution from chiral multiplet, Fermi multiplet, vector multiplet, like this way, okay? And then, yes, then you just combine them together in like this way and perform the so-called Jeffrey-Cowan residue. And this prescription done by Benini, Igor Tachka, Horin, and so on. We follow this method to check the duality. So this is another constraint, how to say, check can be done by using Hooft anomaly, which can be computed by trace of, sorry, what's that? Trace of gamma 3 times this Carlton of the flavor symmetry. That will give you the Hooft anomaly, and that is the ship match under the duality. So that's the Hooft anomaly matching. One of the most important anomaly coefficient is the central charge, which can be computed by this formula. CR is equal to 3 times trace of gamma 3 R squared. R is the charge of U1R symmetry. And then to determine the U1R charges, actually, usually there's a lot of mixture happen in the process of an RG. And then usually C experimentation will be is supposed to apply if the following two conditions are satisfied. First of all, energy spectrum is bounded below zero. Sorry, from zero. And also the second condition is the vacuum moduli is the compact, normalizable or compact. But however, most of the 0,2 theory fails to satisfy second condition. So therefore, C extermination generically does not work for most of the 0,2 theory. And then in this talk, again, all the theory do not satisfy the second condition. So therefore, we cannot apply the C externalization. And in that case, you have to apply you have to set the R charge of chiral to be 1, Fermi to be 0 by hand. And then except one example, which is called 0,2 triality. And then this is the way of computing right moving central charge. Left moving central charge can be computed by gravitational anomaly. So this is essentially just compute the difference between number of the chiral multiplet and the Fermi multiplet. That's how you compute left central charges. Any question at this moment? So these are the tools to check the duality. How I'm going to propose. Under the dual theory should match for this anomaly coefficient and the pictureness that are supposed to happen. Okay, so the first major step on this 0,2 duality is done by these people. Actually, it's not duality in 0,2 duality. So let's try to recall this major step. So it's IR equivalence of 0,2 gauge theory, and the gauge group has to be unitary group, and the matter content is given by as follows. So the one is the N1 fundamental representation Karamant fit, and two anti-fundamental representations. Sorry, somehow I missed the bar. It should be something like I'm sorry, I missed bar here. Sorry, bar here. Anti-fundamental representation, and then so this is a Fermi multiplet with the fundamental representation, and then you have a two determinant Fermi to cancel gauge anomaly. So that's the case, and then in addition you have some mesons, Fermi meson, which forms some J-term superpotential given here. And then the rank of the gauge group is given by as follows: so N1 plus N2 minus 3 divided by 2. And this theory, in fact, you can just permute these N1, N2, N3 to find a different UV description. But in fact, they are the dual to each other in infrared. So that's what the GGP found, which really starts the 0,2 really gauge theory in gauge theory, like a study of gauge theory. Any question at this moment? Sorry, I somehow missed bar here, so this is not correct. Not correct. So I need to put somehow bar here and the bar here and so on. Sorry about it. Somehow I missed the bar. So anti-fundamental advantage. So as I mentioned, so they are dual to each other if under permutation of this one. So N1, N2, N3, if you permute, you get this theory and this theory, and they are due to each other. And this can be understood as the relation of the IR geometry. If you look at the first theory, so N1 is fundamental representation, N2 and N3. Here again, so you have to satisfy the following condition: Ni plus N2 is Ni plus Ni plus 1 is greater than or equal to Ni plus 2, and I is taken to be the mod 3. And then this theory, if the Fi parameter, so you can put the Fi parameter because the gauge group is unitary. Fi parameter is positive, they flow to this geometry. So the Grassmannian of the N3 and 1, and then the S and the Q are the following. So the O to the N 1, and then S is the tautological bundle, and the Q is the constructed by the short exact sequence. So S is tautological bundle, Q is dual tautological bundle. Kind of like, yeah, they constructed this short exact sequence, and then you can form the bundle like this way. And then this, by using the construction of Grassmannian, so this is the equivalent to this construction, which can be understood as the F5 term negative of this IR geometry when this series with F5 term is negative. Okay, so they are the IR geometry equivalent. But however, so if you take the F5 times the negative here, then the IR geometry is flow to the this geometry. So it's now instead of N1, it becomes N2, and then the corresponding bundle is the for this Grassmannian. Yeah. And so this geometry is equivalent to positive Fi parameter for this theory. So therefore, depending on the Fi parameter positive or negative, you can connect the geometry of this theory, either this theory or this theory. And also you have to pick appropriately Fi term here. So this 0, neutrality can be understood as the relation of the R geometry and the Fi term, the sign of the Fi term plays a very important role. Okay, any question at this moment?
So are they discussed as the conformal field series with certain
Yes.
special central charges?
Yes. When zeta is equal to 0, so they flow to CFT. So usually 0,2 gauge theory is flow to 0,2 gauge theory flow to a 0,2 nonlinear sigma model. And then when gamma, so this Fi time parameter is 0, there is no parameter in a theory, so that it flows to the CFT. And this CFT is described by some coset model. So 0, 0,2. So therefore, right moving sector is actually described by Kazama Suzuki. And then here you just left moving sector is some affine Lie algebra or coset model. So, and then the exact partition function is constructed by using elliptic genus and the modularities. That is done by these people.
So Kazama Suzuki model is 2,2 supersymmetric theory, right?
No. Kazama Suzuki is the n equal to 2.
Yes, I mean n equal to 2, right?
Yeah. So the right moving sector is Kazama Suzuki, and left moving sector is some West-Zumino-Witten type. So it's non-chiral. So the right moving is Kazama Suzuki, but the left moving is something different, non-supersymmetric, generical.
But Kazama Suzuki model has two integer indices, right? Just mn, for example, m and k. So how do you connect? So some special indices for Kazama Suzuki model can realize this, or what is the description in terms of Kazama Suzuki model?
Yeah, Kazama Suzuki is so the central charge
What type of Kazama Suzuki model? Is that the A-type Kazama Suzuki?
I don't remember it should be A-type. It should be A-type. I don't remember the detail. But it was
The general Kazama Suzuki model is labeled by two integers. So what are the connection to Kazama Suzuki?
So, but here, you have an N1, N2, N3, right?
Yes. So
that is related to the integer in Kazama Suzuki, but I don't remember the detail. For instance, if as far as I remember, so all the N1 is equal to N2 is equal to N3, it flows to somehow E6 cross SO something divided by something like that. I don't remember the detail. I think you should refer to this GCP. Yeah, E6 with level 1 or something like that. In generically, you have the coset model with the SU with the N3 and I times U1, U to the sum, U1 to the something, and the level is related to N I plus 1 or something like that. It's kind of complicated one.
For example, so elliptic
Mm-hmm.
genus Kazama-Suzuki model is exactly computed without
Mm-hmm.
any subtleties.
Mm-hmm.
So
Yeah.
just
So
like
so
for zero
here
comma.
you can compute elliptic genus, and then they computed the modular invariant partition function for this 0, 2, this coset theory. And once you set the right moving sector and ground state, we can reproduce elliptic genus. That's how they found IR CFT.
You mean starting from the 0, 2 elliptic genus or any partition function, then that is shown to be realized partially by Kazama-Suzuki elliptic genus?
So as I mentioned, so right moving sector needs to be ground state. So for elliptic genus, right moving sector always ground state.
Yes.
But okay, let me write down. So the partition function is something like sum of chiral of left of some q, and then right of, say, whatever weight I and the q bar. And sometimes modular invariant I and j. Let's call j. Modular invariant I and j. So that's how you construct a modular invariant partition function. And what they did is that so here is a character of the Kazama-Suzuki. And this is the character of some affine Lie algebra. Because there is no supersymmetry. But here you have n equal to supersymmetry, and they realize that it's Kazama-Suzuki. And the central charge agree, of course. So if you can compute both central charge, it should agree with the 0 to triality central charge. And then what they did is the set right moving is a ground state. Ground state, okay? Then you can compute, you can reproduce elliptic genus of 0, 2 theory. 0, 2 triality. That's how they identified. So they use the modularity and also central charge to find IRCFT to compare with elliptic genus. That's what they did. Do you understand what I mean?
Not completely, but you're saying that the object that computed in 0, 2 theory is a partition function in this form?
Yeah. So IRCFT partition function is really like complete Hilbert space. Trace of Hilbert space Q to the, okay, let me write down. So this is, sorry. Trace of Q to the HL, Q bar to the H bar R. And then, yeah, I mean, if you want to include flavor symmetry, it's the I, product of Fi. So this is, no, there's no -1 to the F, no -1 to the F, no -1 to F. But to go to the elliptic genus, you have to set the right moving center to be ground state, and you have to insert -1 to the F. But that can be done from this partition function, because it has contain more information. This contains a full Hilbert space. Not only the right moving sector ground state. So elliptic genus, as I mentioned, it has to be, the right moving sector needs to be ground state. And we only just count the left moving sector. Non-trivial. But if you consider the cost of the model with 0 to supersymmetry, and you construct the modular invariant partition function, you can reproduce the 0, 2 elliptic genus. That's what they did, this GGP did in second paper. Okay. Any question? Any other question? Okay, let me move on. Okay, so essentially this triality is like only like a duality known in 0, 2 supersymmetry. I want to add more list into the 0, 2 supersymmetry. And to do that, they use the twisted compaction for the n equal to 1 to the 0, 2. And so I just put the for the n equal to 1 theory on R1, 1 on S2, and do the topological twist on S2 with the U1R symmetry. Then globally on S2, this R charges needs to be integer. So to be well-defined in twisted compaction, it has to be integer and a positive integer. And then you get the 2D 0,2 theory. And then in fact, the n equal to 1 vector multiplet is go to the 2D 0,2 vector multiplet. And depending on R charges of the for the n equal to 1 chiral multiplet, it can become chiral or Fermi, depending on where if R is equal to 0, it becomes chiral. And if R equal to 2, it becomes Fermi. Then if R is greater than 2, it just give a bunch of Fermi. Any question at this moment? Essentially, it's R
But
one
you want R charge for chiral must be an integer, means that so if you think about the free chiral multiplet, then it has like a 2-third, right?
Yeah.
So that cannot be put on this setup.
So you cannot put the integers. Yeah, you cannot do the well-defined topological twist for that one. So you have to reassign in R charge in such a way that they satisfy this integer condition, integral one. That I will explain how you reassign R charges inconsistently. Any other question?
Yeah, for U1, sorry, 4-dimension equal 1, so we use A maximization to determine
Yes.
the
Yes.
central charge. So then we have additional like a U1 charge, and then so it's kind of mixed in, contribution appears.
Yeah.
So
So
then, how do you
usually so this fractional one you cannot do the S2 like a twisted compaction on S2, but so you have to somehow reassign the integral R charges inconsistently, which and satisfy some vanishing of the gauge anomaly condition. That's what you need to do. So I will explain that later, how to do that.
Okay.
Any other questions? Okay, so another way to get the 0,2 is that going from for the n equal 2 to the 0,2. To do that, so you start with for the n equal to 2 SCFT, which has the SU2R cross U1R symmetry. And then we just consider diagonal subgroup of U1R, which is the carton of SU2, and then U1 small r, and twist it with U1S2, U1S spin 2. If you do that, so as you can easily see, so this is the U1 capital R charges, and you twist with the 1/2 of the U1R, and then twist with the S2. So you twist with this. So 1/2 plus 1/2 minus 1/2 minus 1 is 0. 1/2 plus 1/2 plus 1 is 2, like this way. Okay. And what the supercharges that survive is of course the 0 supercharge. And if you look at the charges of the -1, this means the right moving sector. So therefore 0, 2 is supercharge survive. But if you look at the Lagrangian, so you have to be careful because I mean, as I mentioned, the R symmetry needs to be integer. So if you have a 1/2 plus 0, and here 0, so therefore you only have a 1/2. So therefore you have to further twist by U1 F supersymmetry, your flavor symmetry, which is written here. So 1/2 and 1/2, which is +1. And as I mentioned, +1 R charges does not survive. I mean, R has to be greater or less than 1. So therefore, this does not survive under this twisted compaction. On the other hand, you have a 1/2 minus 1/2 plus 0 and plus 0, and you get the sorry, I just did something stupid. Okay, sorry. So 1/2 and minus 1/2. Okay, so this is, you have to multiply minus 1/2 for U1 flavor symmetry, and then you get 0. So this one is survive because it becomes chiral multiplet because R equal to less than 1, and 1 minus 0 is anyway, 1 chiral multiplet. So this one survive. So therefore, this becomes 0,2 chiral multiplet. Okay. And on the other hand, if you 1/2 plus 1/2, you give you 1. So this does not survive in okay. And also here you have 0 and 1 and whatever 0 and 0, you get 1. So the adjoint color does not survive. So you have so from here, what you get is the n equal 2 vector map, you give 0,2 vector map, n equal 2 color map, you give the 0,2 color map. So under these compactations, for the n equal 2 SCFT to the 0,2 series. And in fact, the reason why I consider SCFT is that the beta function, vanishing of beta function is really equivalent to gauge anomaly free condition. I mean, this, if you compute this one, it's really equivalent to the gauge anomaly vanishing condition. Okay. And in fact, under this reduction, if you write down the elliptic genus for Lagrangian SCFT, integrand of 0,2 elliptic genus really match with Schur index of the original for the n equal 2 SCFT. The Schur index is supposed to be unit circle integral, but 0,2 is the JK ratio. That's the difference. So
I have a small question. So what
yes.
is for the n equal to chiral multiplet? Is it for the n equal to hyper?
Oh, sorry, hyper.
Okay.
Yeah, hyper.
Also, could you go back to the previous slides? Next, before this one. Yes. So if you consider the chiral multiplet with R charge 2, so the supersymmetry is broken. So what happens for two-dimensional 0,2 theory? So if you take just R equal to
2, then it becomes Fermi.
Yes, then so the supersymmetry is still kept.
Yes.
In 2D.
Yes.
But 4D, so supersymmetry is broken, right?
I will explain. I mean, you artificially put the R charge to be 2.
If you put just a linear superpotential for 4D n equal 1 chiral multiplet, then you know this just the supersymmetry is spontaneously broken.
Yeah, I understand. But you just put the R charge to be the integer by hand. So without forgetting about the physics.
Forgetting about physics, okay, then?
Yeah, by just performing topological twist.
Yeah, but my question is, if you start from this 4D n equal 1 with R equal 2, then you may get some like a Fermi, but is it supersymmetric or not?
It should be supersymmetric. I mean, it just use the how to say, the well-defined topological twist on S2. So that's what I wanted to do. So you just So you just reassign the R charge in such a way that it has to be consistent with S2 compactation. That's what I'm going to do.
But also two-dimensional cases, you can fix the R charge by some superpotential, right?
Yes. I'm going to explain. Don't worry. By Seiberg duality.
Okay.
Yeah. Okay. Any other question? And somehow if you do this, I call it 0-2 direction of for the n equal 2 SCFT, somehow the resulting gauge theory is always due to Landau-Gism, 0,2 Landau-Gism model. I don't know why. I really want to know why, but somehow no exception. That's the observation so far.
So another question is about so n equal 1 SQCD. For n equal 1 SQCD in 4 dimension, we have a conformal window. Some ratio of center charges limited.
Yes.
So what about the 2-dimensional 0,2 theory?
Yeah,
this is similar condition on center charges.
Yes. This is exactly. Yeah, it has the same same phenomena happen in 0, 2 and then 40 n equal to 1. Yeah, so
For
you need
example,
to
if you
consider,
start from, for example, if you start from 40 n equal 1 SQCD with SU n gauge group, and maybe 2n plus 2 chiral multiplets, then this is some sort of a confining description. But if you increase n, then the ratio is actually outside of the conformal window. So lowest bound of the ratio of central charge is satisfied by, I think, only SU2.
Yes, you're right.
So then, what
That
happens
exactly
to the
that
0,
exactly happens. So you have to consider this really the conformal window to get the 2D 0, 2 theory with the positive central charge.
I mean, even for positive condition is, I think, weaker. Weaker. So even they are positive, A and C are positive, so the conformal window is more constrained.
Yeah, and then if you consider you say SUN with 2n flavor, right?
2n plus 2 maybe.
2n plus 2 is the
I
case.
think. Or I mean, 4-dimensional n equal 1, right?
Yeah.
For example, SU2 with 6 flavors in n equal 4, n equal 1, then this is a confining.
And then that will give you somehow lambda gives the dual to lambda.
That is a free theory description. I mean, it's
Yes,
confining.
yes.
But this is, I think, so the A and A over C is half, just 1/2. This is the lowest lower bound of the n equal 1 CFT.
Yeah, and then even that one, even 0,
That
2.
may be,
0,
that may be
2.
fine, but if you consider SU3, SU4, then this
even
lower bound is not satisfied.
Yeah, so 0, 2, this 2C compactation somehow does not work.
Does not work.
Yeah. So you cannot find any duality and so on. Yeah.
I see.
Yeah.
But I think so such conformal condition is necessary to this twisted compactification.
Yes, I think so. I don't remember the detail. Yeah.
Okay.
Anyway, I will explain that this is exactly what the example you mentioned. So let's do the reduction of duality. So let's consider gauge group SU, not unitary. Electric side, this is the 40n equal to 1 charges, matter content. And as I mentioned, so these are fractional. Okay. And then as I mentioned, so the R charge needs to be integer, so that we just reassign the R charge in such a way that this mixed gauge anomaly condition, the imposing banishing of the mixed gauge anomaly condition. So this banishing of mixed gauge anomaly condition will just give you constraint R charges, which will give you like this way: R plus R theta should be equal to 2 times NF minus NC. And then the way you reassign the R charge is to be integer. So the consistent way which satisfies this condition is like this way. All the how do you say? Here is the fundamental chiral multiplet is stay 0, and the R theta is you just assign the NF minus N and C minus N. N is some post non-negative integer. It's 2, and then 2n to 2n chiral multiplet to 1, and then the other is 0. So you reassign these R charge like this way which satisfy this condition. So you can easily see that the 2 times NF minus NC minus N plus 2N is equal to 2NF minus NC. So that satisfies this condition. Okay. And as I mentioned, so this 2 will give Fermi, and then 0 will give you chiral, and then this will become 0, 2 chiral. So this part is this one is just fundamental. Sorry, I should add the fundamental like this way, and anti-fundamental is the coming from what was it? Coming from this part, and then Fermi is coming from here. So that's the electric side. So this is 4D and this is 2D quiver diagram. And if you go to the magnetic side, you can easily see that the similar condition needs to satisfy. So you reassign the R charges in such a way that it satisfies vanishing of the mixed gauge anomaly condition, which is like this way. And then we again reassign this fundamental R charge fundamental chiral to be like this way. Then the resulting quiver 2D 0,2 quiver diagram like this. Okay. And you can compare between these two theory, electric side and magnetic side, by just swapping this Fermi meson into the other side, and what you get is like this way. So I just rename the rank of flavor and then symmetry. Rank of person N1, N2, N3 to compare with the 0 to triarity. But here, again, the gauge group has to be SU, not unitary. Okay, and then if you swapping method relabeling, you get the 2D 0,2 duality. And then here you can just check all those RG invariant quantity to be the same. And yeah, so you can find the duality with SU2, SU gauge group. And then rank of gauge group is given like this way. So it's okay. And the important thing is that it should satisfy this condition. N1 is greater than or equal to N2 plus N3. This is intrinsically different from the 0,2 triarity. 0,2 triarity, you have to have Ni plus 1 is greater than Ni plus 2. Okay, so therefore it's really opposite. Any question at this moment? Okay, so the reason why I'm talking about just flip this Fermi to the other side is that I just really want to compare with the 0,2 triarity. We try to extend this 0,2 duality to triarity, but we fail. But there's an intrinsic difference between unitary gauge group and special unitary gauge group. So first of all, as I mentioned, rank condition for SU duality is incompatible with triarity constraint. That's the case. So therefore, you cannot simply permute the N1, N2, N3. So the rank, as I mentioned, in the Ni plus 1 plus, in triarity, you need this condition divided by 2, the rank of gauge group. And then this become negative because of this one for special unitary. So that the rank become gauge group rank become negative for SU. So that's why SU duality cannot extend it to triarity. That's one way. And also for 0,2 triarity, Fi term, as I mentioned, play very essential role connecting different geometry in phases. But for you cannot SU gauge group you cannot introduce, so that you cannot connect the different geometry. So therefore, SU duality here somehow cannot extend to the triarity. So that's an intrinsic difference in unitary gauge group and special unitary gauge group. So yeah, so this explains why the triarity holds only for unitary gauge group, while it fails for special unitary group. Moreover, so this theory, these two theory is flow to the this nonlinear single model with same target geometry. The duality can be explained by the equivalence of the IR geometry. And here, because of SU, so you need to add some determinant bundle of the determinant bundle of the tautological bundle. Okay. In addition to the what we saw in the 0,2 triality with the unitary gauge group. Any question at this moment? Okay, and then so here if you look at the N1, N2, N3, so N1 is parameterize this geometry, N2 parameterize this bundle, N3 parameterize this bundle. Anyway, so all those chiral and Fermi parameterize the non-compact has a non-compact direction, so we cannot think it violates the assumption of the Seek externalization. Seek externalization requires the vacuum moduli needs to be compact. Okay. On the other hand, for unitary gauge group, in that case, non-homogeneous current appear for Fourier symmetry. So you cannot mix it with R symmetric current. The C externalization cannot apply. So we have to set the R equal to 0 to be current multiplied, R equal to 1 to Fermi multiplied by hand, and compute the central charges. And that will give you like this thing. Okay? And then these two theories, they agree. And in fact, this central charge, right moving central charge is 3 times complex dimension of this target geometry. On the other hand, for unitary gauge group, you don't have this determinant S. So therefore, one of the fundamental chiral just parameterize compact Grassmannian. In addition to that, you have, as I mentioned previously, you have the J-term constraint for the priority theory. So in that case, so unitary gauge group, you have to apply C externalization. So that's the main difference between unitary and special unitary in 0,2 war. And then, in that case, for unitary gauge group, you have to apply C externalization, and you get some fractional central charge, and that match with for right moving, you can identify corresponding Kazama-Suzuki theory, and left moving, you can find the corresponding affine B algebra. That's what GGP did. For special unitary, we check all the truth anomaly matches between these two dual theory, and also elliptic genus also agree. That's we checked. Any question at this moment? Okay, that's the reduction of special unitary Seiberg duality to get the 0,2 duality. Furthermore, you can change the gauge group for Seiberg like duality. You can just change the duality SP gauge group. So the SP any equal to 1 duality with the SP gauge group is found an integrator polar. And then you can just do the same 0-2 reduction to twisted compaction S2 to find a duality. In this case, you can just only find the gauge and then lambda gives duality. You cannot find the SP gauge dual to SP gauge somehow. I mean, this is somehow, if you do the twisted compaction on S2 of the SP gauge group, this is natural consequence of that. So far, there is no duality as found with gauge duality with SP gauge group. So this was found by these two people, but we can generalize this Seiberg duality to somehow triality. So we know the oh, sorry, this is SU. So this is not SP, SU. We know the since SU with 2n gauge, SU 2n with antisymmetric and 2n plus 2 fundamental is a super conformal. And then you can just do 0 to 0 reduction of the this n equal to SCFT, somehow we realize that they are dual to these two theories. The one you obtain for SP Seiberg duality, Seiberg-like duality for the n equal to 1. So we found that the three theories are dual to each other. One is the SP with 2n plus 2 fundamental chiron with no superpotential. The other is the SU2n gauge theory with antisymmetric and 2n plus 2 fundamental chiron. And you add the sum Fermi to form this superpotential. That is dual to the somehow the Landau-Gibbs model, n plus 1 to n plus 1 chiron with superpotential like this one. So those three theories are dual to each other. We check the two normal matching electric genocyclicity for these three theories. Any question at this moment? That's the neutrality. And we can do the same game for SO gauge group. If you reduce the for the n equal to 1, integrate the Seiberg duality with SO gauge group, you can find 0,2 duality. You have to add appropriately like some Fermi and then the free chiral, neutral chiral to form this superpotential on this his side. And then if you consider 2C compactification of, again, I made a mistake. So this is SU and gauge theory with one symmetric and then 2n minus 2 fundamental hypermultiplet. In fact, for the n equal 2 theory is because super conform. And you can do the 0,2 reduction of this theory. And we realize that they are dual to this theory. So therefore, we can somehow combine the n equal to 1 Seiberg duality with the for the n equal to 2 SCFT compactification. You can find somehow triality, neutrality, like we did in SP gauge. And then superpotential is given like this. Any question at this moment? So these are neutrality we found from for the twisted compactification to the 0,2. And then so what we found so far.
In 4 dimensions, so some line operators can distinguish some SO and gauge theory. So can we expect to have similar story for 2D?
Yes, I think you can. You mean SO spin? You mean?
Yeah, or maybe pin or etc.
Yeah, I think so. So far, we didn't check so much detail.
Okay.
Yeah, I think if you add the line operator, maybe there may be subtle difference may occur between these two. So you need to maybe adjust this triality to add some non-local operator. Okay, so these are what we found from for the n equal to 1 or n equal to 2 2C compactification to the 0,2. So far we found somehow duality with SU gauge group, and then I call it this is the triality with the here antisymmetric. So I call it the antisymmetric dual. It is dual even though it's triality. I have another symmetric dual. So and then using these three duality as a basic building block, we can find somehow new duality from these three dualities. That's what we are going to do from now. So for instance, let's see. I just want to add so here you have the fundamental chiral, but I just want to add the here in the Fermi. And what's going to happen? That's what I did for. What's going to happen is duality. That's first motivation to consider this theory first. But you can just use AS still to reduce the rank. So as you can easily see, this is 2n plus 2, but this is 2n, right? 2n. So therefore, you can just 2n is just the antisymmetric is 2n minus 2 and one antisymmetric and become like 2n plus 2 if you apply this relation and so on. And if you do that recursively, you will get this one. And at the end of the day, so SU one antisymmetric, this is trivial. So therefore you get some free chiral. And furthermore, you just apply this block to be in this SU dual and just flipping these by using this chunk into the left. At the end of the day, you will get this theory. You get this theory. And then there is some subtlety. If you compute elliptic chains, they are not indeed dual to each other because of some subtlety of fugacity. But if you fix this free chiral and then this antisymmetric, they really become dual to each other. So therefore, what we found is that applying this chain of duality, and then we found this is quiver theory, SU quiver theory, and then SP some gauge theory are dual to each other after Higson. So this is new duality, and of course somehow you have to impose some nice superpotential in J-time superpotential in this loop. And here we again check that root normal matching elliptic chain agree. Yeah, we can do the similar game. So you start with the SUN with antisymmetric with bunch of chiral, fundamental chiral and anti-fundamental chiral, and some Fermi, and so with some mesons. And then you just consider the apply. So still here to still which is given here. So this is dual to this one, right? So we can do the same game in here. So here you just apply AS dual in this chunk to get this duality, and further apply this chunk to the SU dual theory, and then change the rank of the SU gauge theory, and then again apply AS dual, and end up with the very similar configuration, but the rank is different. Rank is different. And then we check they are dual to each other. And this duality is in fact the generalization of this, I think Amariti and the company has found. Huge generalization they found. Some special case of capital N, small n1, and small n1, they just reduced to what they found. But here it's much more general still. And then you can play the same game for symmetric matter. Again, do the same chain of duality apply. You can find the new duality with the SU gauge group with symmetric matter. With some certain condition that needs to be satisfied. Any question at this moment? Okay, another duality is that so gauge lambda gauge duality. Here you have the 0,2 vector plus 0,2 chiral in a joint representation. So which means this is 2,2 vector. Not vector. And this is actually 0,2 reduction for the n equal to 4 here. 0,2 reduction on S2. You get this one, and if you they are indeed dual to the rank G free chiral multiplet corresponding to the place of phi to the R. Phi is the adjoint chiral. So this is actually flow to the free theory. Free. And the similar thing happen. So if you consider this kind of SUN with symmetric and anti-symmetric with bunch of Fermi field and some complicated superpotential which I suppress because it's not so important. And they are due to Landau model with this amount of chiron and this amount of Fermi and with some non-trivial superpotential. That's what we found from the 40 n equal to 2 SCFT compact to the 0, 2. Sorry, to the 0, 2. Zero.
Great. So I have a question.
Yes.
So the first example is 2, 2, just a pure amuse, right?
Yes.
I think this was already discussed by Haroni and his company, I think.
Yeah, Aharoni and the Cyber
Cyber, yes.
and then the Willet and the Razamat. I forgot, long flow to freedom, something like that. Yeah.
Well, this is already known, right?
Yeah, this is already known. But this another way to derive this one is the twisted compactation for the n equal to 4. Yeah.
But is it really conformal?
What do you mean conformal? Which side is conformal?
I mean 2, 2 theory with just a pure amuse.
Yeah, of course it's not, but it just flow to the nonlinear sigma model. It's not conformal, but it flow to nonlinear sigma model with C to
But
the
you said
rank
that some
of
condition
gauge
like a
group.
twisted convolution only applies for conformal case, right?
I mean UV 0, 2 I consider is always not the conformal. It just flow to the nonlinear sigma model.
You mean starting from just a maybe result, it may not be conformal, even if you
Yes,
start
yes,
from.
yes, yes.
Oh, I see.
Yeah. 2D 0, 2 theory. You have just UV description as the gauge theory, but they flow to the nonlinear sigma model. In this case, just C to the rank of G.
Yeah, just check your paper. So you
Yeah.
said some center charges are computed
Yeah.
for this. What do you mean by center charges?
Central charge is the CR is a 3 times dimension, complex dimension of the vacuum moduli.
Yeah, but in your paper, it is said to be rank or something, not dimension. Is it typo?
I don't know which part I'm talking about. But I
Maybe
mean,
I can tell you later. Yeah, but anyway, so some center charges are not, I mean, does not make sense, right? This is not conformal. It's just two anomaly.
yes, it's a two-foot anomaly, and which is a 3 times dimension of the target
I
space.
think
That's true.
minus 3 times dimension, not plus 3. If you say like this conformal, I mean, just two anomaly computation, there is not positive. It's negative, right?
No, it's
If
positive.
you just compute just a two anomaly.
It's positive.
Why? Because if you,
Trace of gamma 3 and
I mean, this was
then
already
R squared.
discussed by, I think, Eric Sharp and his collaborators. If you think about to come to pure amuse, then effectively you can compute some tooth anomaly as a negative values and minus 3 times dimension. But this is just tooth anomaly.
Okay. But here, I just compute you just decompose the 2, 2 pyramids by 0, 2 language, and the CR you just compute it by R squared, like this way.
Yeah,
This
that's
is
the same.
CR.
Yeah.
Yeah.
Yeah, it's the same. I mean, yeah. I mean, just a CL equals CR equals C, right?
Yes. And then this become positive once you set this to be 0, R to be 0.
So left and Y is positive.
Because the sum of
I think
1
this can be
minus
also
r.
computed from right-hand side. I think if you start from like a twisted chiral MOSFET with a shifted
Yes.
R charge,
Yes.
then I guess that you can easily compute the center charge by fixing R charge.
Yes. That's exactly what we
And I
did.
don't think, yeah, I mean, just remembering the result of this Eric Sharp and his collaborators, so they conclude that this is a negative value.
Okay.
But maybe, yeah, maybe I can discuss later. But anyway, yeah.
Okay.
So this is just my question, yeah.
Okay. Anyway, so if you set the trace of gamma 3 r square and set the r charge to current to be 0, and then you get the CR is 3 times the dimension of target space. That's what we did. Okay, so those are the paper I mentioned at the beginning, the result on. But I just briefly, okay, running out of time. Is it okay to? I already 7 minutes.
Yeah,
Or if you
sure,
want,
yeah.
if
You
you want
can go
to,
ahead, yeah. You
okay,
don't need to care about time,
okay,
yeah.
time.
It's
Okay,
just
so I think I will go 10 more minutes. I mean, you can little bit discuss about the 0, relation between 0, 0,1 and 0, 0,2. So the GPP discuss the triarity with minimal supersymmetry, 0, 0,1. And 0, 0,1, the gauge group needs to be either SO or SP, because the representation needs to be real. And then they consider the following: the matter content, so 2 scalar and 3 Fermi, with this can be depicted by this Kuiper diagram. So you have the 2 scalar and 3 Fermi, and they form this superpotential. And they be proposed that they are very similar to 0, 0,2 triarity. And they are dual to each other under the permutation N1, N2, and N3. Okay, and they check the elliptic genus agree and so on. Also, the two may agree. And then this triarity can be understood as the relation between IR geometry. And then instead of the Fi term, they put this capital C to play the role of the sign of this, depending on sign of C, they flow to different phases of the geometry, which I'm going to suppress. It's just the real version of what I show in 0, 0,2. And then recently, they just GPP actually compute the elliptic genus by just performing this kind of usual like vanilla type Attia bot localization on the target geometry to compute the elliptic genus or like a Witten. It's just original. Date back to Witten. But recently, Junya and then the CPU people proposed that the elliptic genus 0, 0,1 elliptic genus can be computed by even using UV description. And they perform the Jeffrey Cohen residue integral to the UV description to compute the elliptic genus. And that is a result. And if you stare at this elliptic genus, in fact, this elliptic genus agree with the 0, 0,2 theory, which is written here. So you just consider unitary gauge group. This is 0, 0,2 theory, not 0, 0,1. With the say fundamental and anti-fundamental and Fermi meson and form of superpotential. In addition to that, you add one more chiral with its fundamental both UN gauge group and then the Freiberg gauge group, and same thing. You doubling the Fermi and then chiral It's the same thing you should do for here. And the compute elliptic genus. If you compute the elliptic genus exactly, it just exactly agree with this 0.1 theory. So since the original 0.1 elliptic genus is invariant under a permutation of n1 and n3, so the elliptic genus theory is also invariant under permutation n1 and n3. So it seems like this theory also enjoy the triality. Somehow just staring at the 0.1 elliptic genus and interpret it as a 0.2 theory, somehow you can find, is it kind of question mark? But seems that's valid operation you can do. And then seems this is new 0.2 triality, which is not included in our paper, but we just observed that. Any question at this moment? So since the time limit, I didn't consider the other discussion we did in the paper with Jiaqun and Jiahao. We also talk about somehow the different twisted compactation for the n equal to 2 SCFT. So if you twist between the one I talk about today is the diagonal of U1 capital R and the U1 R that leads to 0.2 theory. But in fact, you can twist by U1 capital R that will lead to the n equal to 2.2 theory, or you can just twist by only U1 small r to get the to the 0.4 theory. And then in particular, if you consider classes theory as a parent theory and do this kind of topological twist, in fact, somehow the resulting two-dimensional theory enjoy the as you expect, the original theory just enjoy the S duality. So therefore, their ancestor not ancestor, sorry, anyway, to the sons or daughters, kids are also satisfied this kind of S duality. So we just compute elliptic genus for different frame of the class set theory, and we realize they are dual to each other. Furthermore, all those different supersymmetry, they somehow elliptic genus showed a surprisingly simple form, which is just some bunch of products of theta function for genus contribution and bunch of product of theta function for function contribution, and they somehow exhibit TQFT structure on linear surface. Okay, so this story is due to time constraint, just omit, but I just want to introduce if some audience are interested in. You can take a look at our paper, the Yuan and the Jiahao and Jiaqun and Jiahao. That's what we found. So this is just brief introduction of some other story. Okay, so that's what we did for 0.2 theory. And as I mentioned, there are lots of open problems. So the question is, can you find some brain construction of brain interpretation by brains in string theory, or what we found for 0.2 duality or new 0.2 duality or triality for geometric engineering interpretation? And also, 0.2 triality has been interpreted as from the perspective of integrable model by Junior and the companies. Can we find similar integrable structure? There's even paper today or yesterday talk about this kind of stuff in 0.2 theory. Can we find a connection to 0.2 theory and the integrable system? I think what we found is the really tip of iceberg. There must be more 2.2 duality and 0.2 duality, but somehow we just lack the tool. I think I only did perspective from the twisted compaction for the theory, but there must be more many ways to approach the duality in 2D theory. And also another interesting topic is 0,2 enhanced to 2,2. That is the, I mean, you can obtain for the n equal to 1 enhanced to n equal to 2 if you end on S2 compactation. That you can obtain 0,2 to 2,2 supersingle enhancement. And yeah, so other things you have to you can many things consider, but I just leave it these problem to open problem to audience and then finish the talk. Thanks for attention.
Thank you very much for a nice talk. So now we have time for question and discussion.
Yes.
Is
Yeah,
there any
please, yeah, please, audience, if you have
comment?
some insight, please tell me. Yeah, one thing is the 2D boundary condition of 3D n equal to 2 theory. Can you construct new 2D duality? That's also like what I asked the Tadashi is that if you consider 3D n equal to 2 theory and then 2D 0,2 boundary condition, so like this way, can you find that if you use duality in 3D n equal to 2, can you find the duality in 2D 0,2? That's one question one way to construct the 0,2 duality.
Yes, so I think
Yeah.
in principle this is very useful to find the new duality for by starting from 3D theory. But there's still kind of a difficulties to proceed. Yeah, how we can consistently decouple 3D degree freedom. But I guess interesting theory is just a combined 3D and 2D systems and to see the duality maps in both bulk and boundary systems. So, but actually, yeah, I think this is very interesting question and
Yeah.
But is there any other tool to just test the duality you claim? I mean, not only LP genus, but also any
Yeah, I
certain.
think, yeah, I mean, in principle, originally, like was Cyberg and then for the n equal to 1 duality has found, maybe you can perturb the superpotential by adding some mass term or something like that in both sides and flows to like change the rank or gauge group or flavor group. That's one way to like check the duality. That's another way to, yeah. Which we didn't do that. We are too lazy to do that. So I think we should have them.
Yeah, also another question is about holography. So is there any application to see gravity dual descriptions from your case theory?
Yeah, that's a good question. 0.2, how about 0.2 triarity? Does anybody study large n limit of 0.2 triarity and so on? I think this is, yeah, very interesting question. First thing we can do is this 0 to triarity, and then since the SU duality is very similar to 0 to triarity, maybe we should start with the large n limit of 0.2 theory of this. That's, I think, does anybody study that?
For example, starting from this construction of just in terms of M5 range, and you may have some nice maybe set up to predict some duality gravity dual, right?
Yes, yes. So some of the duality can be interpreted M5 on Riemann surface Gn times S2. Yeah, NM5. So that's the, yeah, you can construct 0, 2. So,
Unlike the case of 2 comma 2, so like a 0 comma 2 theory, I think if you look at the Cadillac behavior of the AP genus, then it
mhm,
may grow as just exponential growth may appear due to the usual, yeah, similar phenomena as Cadillac, usual Cadillac behavior.
that's true. That's true. That's true.
That would say that we could see any, yeah, some check
Yeah,
from the
yeah.
side.
It's very good question. I mean, very good question. And yeah, some of the elliptic genus, 0, 2 theory, elliptic genus, and they apply the S duality, or like a tau goes to -1 over tau, and then do the saddle point method to get the, yeah, Cardi-like behavior. Like some theory works to read off the central charge CL, but some theory, most of the theory does not work somehow. I don't know why.
What do you mean that it does not work?
So usual story of 2, 2, I mean, you just apply.
Yeah, I mean, 2 comma 2 case, I think we have just C equals CL equals CR usually.
Yeah, yeah.
Therefore, leading behavior is captured by the difference of CL and CR, so therefore the leading term is just vanishing.
Mm-hmm.
But if they are different, I mean CL or CR are different, then we could see the leading exponential growth. That's the case for 0 comma 2, or maybe 0
Yeah,
comma 4.
but if you consider like a QCD type like this way, it's okay. But if you add some adjoint chiral and so on, somehow, oh yeah, that's I think exactly what you mentioned. I mean, for instance, this theory. So for instance, if you consider this theory and you consider elliptic genus,
Yeah, so this case,
computing.
I know elliptic genus is a bit trivial. I mean, just a twisted chiral match with elliptic genus is a
Yes,
problem.
yeah,
And then
yeah,
it does not grow as exponentially. I mean,
yes.
it's a so we have a cancellation of bosonic and fermionic excitation in
Mm-hmm. That's true.
denominator
That's true.
and numerator. So,
That's true. That's
but
true.
I'm asking about some phenomena, fit the behavior for 0 comma 2 elliptic genus you just
Mm-hmm.
computed.
Mm-hmm. Yeah, I think those QCD type should be okay because somehow gauge group is somehow completely broken. But for generic like gauge theory with other joint and so on, U1 gauge group is unbroken. Somehow elliptic is like Cardi-like behavior. Somehow you cannot, even if you take the Cardi limit and so on, I mean you cannot read off the central charges in 0, 2.
Yeah, for 0 comma 2 theory, is there any theory which maybe I think, yeah, this is actually very, yeah, because the original, uh, yeah, Gadegugov Petrov paper
Mm-hmm.
discusses the UN, I mean SQCD with UN group triality,
Uh-huh.
and the dual description, it's like a confining type description is given by Fermi multiplets rather than chiral multiplets,
Mm-hmm.
and then that ape genus does not uh, grow exponentially.
Yeah.
So, but in this case, if you take the chiral multiplet description, then
Mm-hmm.
it may not be a good index or good ape genus when you turn off the fugacity because of non-normalizable bosonic modes. It
Mm-hmm.
diverges, right?
Mm-hmm.
So that is rather different from like a 40 index and 60 index.
Yeah. Yeah. So like somehow it I mean if you find some very nice theory, you can find the exponential growth and then you can read off like a Cardi-like behavior.
I mean, is
But
there any nice theory which has description in terms of 0, 2 chiral multiplet with non-zero R charge?
non-zero R charges.
If you set R equals 0,
Oh
then
yeah. Mhm.
so if you take unfavored limit, the elliptic genus diverges, right?
Yes, because it's just elliptic genus is just how to say, like just describe the nonlinear sigma model. So it's a kind of like it should be related to some elliptical homology of nonlinear sigma model. So it's more like a necklace partition function. It's just this elliptic version of necklace partition function. So it's not just yeah. If you set the flavor symmetry to be zero, or like flavor chemical potential to be zero, it diverges. Yeah, you're right.
Yeah, in this sense, so it's difficult. I mean, this is due to the, I think, non-normalized of zero modes.
Yes,
So if
yes.
you remove this, and it may be a good function as just a counting function.
Yeah, that's true. Yes, I think this duality is the good example where Kara is R charge non-zero. So duality, I think you can consider the Cardi limit also large limit because I mean here it's just IRCFT is well understood because thanks to the GGP. The left moving is affine Liajoba, right moving Kazama Suzuki. So I think this theory should be able to understood in LACFT context. For the other theory we consider is I don't know how to interpret the CFT context, to be honest. It just flows in a nonlinear sigma model. How do I don't know how to interpret it in the like. So that's why open question is the relation to chiral algebra. What was it? Open question is the relation between elliptic genus and chiral algebra character, which I don't know. So I don't know the CFT interpretation of the theory.
I mean, do you expect, so what do you expect the relation between elliptic genus and chiral algebra characters? Is there any example to see this
That's
relation?
only like a 0 to triarity, as I mentioned. So
I mean,
during
just
the talk,
okay, the GGP paper.
yeah, that is the only theory
Mm.
IRCFT algebra characters understood.
Mm.
So the other we don't know. We only know the nonlinear sigma model. Uh, uh, and then you consider the elliptic genus of this nonlinear sigma model. That's why I mean if you set the flavor symmetry,
Could you
so no
also
flavor velocity.
could you also show the center charges that you show in the slide, like a label by gauge ranks and flavors?
So for instance, here.
These so these are also integers, not fractional.
Yeah, yeah,
So for
yeah.
2, 3, if you have these kind of integer center charges, then if genus can be understood as maybe weak Jacobi form. And how about for 0, 2?
0, 2. Yeah, I mean here it's just 3 times the dimension target space, and then here the
Yeah,
difference
this
is
is
just
the
around.
usual. I mean, 3 times dimension. This is yeah, I think
Yeah,
expected for 2, 2
yeah,
story.
yeah. And then difference is just a bundle over it. This Fermi bundle, like a left moving Fermi bundle over it. But the relation to electric genus, to be honest, I don't know. Okay,
So
so the
then,
answer is I don't know. I didn't take Hardy limit or like take the S transformation and then the saddle point method. But somehow some theory works to read off the central charge, but some theory doesn't. Do not. I don't know the reason, to be honest.
mm,
Okay, audience, do you guys have questions? Or do you guys have a suggestion to me? Does anybody know what how to construct zero-two theory by brain and so geometric engineering except this Sebastian and company did? As I mentioned, I'm kind of desperate for suggestion. If the audience can give me some suggestions, that would be very nice.
Or any point, if you have any question, please.
Yeah. There are many audience still. Okay. If there isn't.
Any normal question or comments? Maybe we can discuss after. Yeah, maybe we can formally stop.
Okay.